In April 2026, three separate Chinese artificial intelligence laboratories released coding tools within a 2-week window. Each matched the best Western models on standard benchmarks. Each shipped as free open-source software. Each undercut Western pricing so aggressively that developers in Lagos, Kuala Lumpur, and São Paulo had no financial reason to choose anything else. This was not a single breakthrough. It was a pattern, and the pattern has intelligence analysts, technology executives, and defense strategists revising assumptions they held with considerable confidence just 18 months ago. The dominant narrative inside Washington policy circles and Silicon Valley boardrooms has been consistent. China trails the United States in artificial intelligence by somewhere between 1 and 2 years. That gap, the argument goes, provides sufficient runway for American firms to consolidate their lead, for export controls to bite, for the structural advantages of open democratic research ecosystems to compound. The gap is real. The runway is narrowing. The structural advantages are being contested in ways that have little to do with talent pipelines or venture capital. What is closing the distance between American and Chinese AI is not what most analysts predicted. It is not a sudden influx of compute. It is not a talent drain from American universities. It is something harder to quantify, and for that reason, harder to counter. Software engineering ingenuity applied specifically to the constraints that policy tried to impose. The story of how China's AI closed 18 months of distance faster than expected is also the story of how a defensive improvisation became one of the most consequential strategic postures in the current technology competition. It did not begin as strategy. It began as necessity. Eric Schmidt spent years as the executive chairman of Google and later led the National Security Commission on Artificial Intelligence, a body that produced a 756-page report in 2021 warning that China was mounting a serious challenge to American AI leadership. Schmidt's assessments carry institutional weight. In 2025, Schmidt placed China 1 to 2 years behind the United States in frontier AI capability. That estimate was already more compressed than the comfortable 5 to 10-year leads that American technologists had assumed existed as recently as 2020. By 2026, Schmidt revised his position again. China, he said, was within 6 months. He described that interval as a nanosecond in our world. That compression from 2 years to 6 months in roughly 12 months demands explanation, not because Schmidt's assessments are infallible, but because they reflect a broader pattern of analysts across government, academia, and industry arriving at similar conclusions around the same time. The 18-month figure that circulates in policy discussions is itself a measurement artifact as much as a technological reality. AI capability gaps are assessed through benchmarks, standardized tests that measure performance on coding tasks, mathematical reasoning, language comprehension, and multimodal understanding. The results are highly sensitive to which benchmarks are used, how they are configured, and which versions of models are being compared. A gap that looks like 18 months on one benchmark suite can look like 3 months on another. American models have historically led on benchmarks developed primarily by American institutions, using evaluation frameworks built around American research priorities. Chinese laboratories have become increasingly sophisticated at both benchmark performance and benchmark selection. When Alibaba's Qwen model surpassed Meta's Llama as the leading open-source AI model in late 2025, the comparison was not abstract. Qwen had been downloaded approximately 1 billion times. Developers worldwide were running it, building on it, and integrating it into production systems. The benchmark performance was being validated by actual deployment at scale. The gap has always been partially a matter of where you look. By 2026, more and more measurement approaches were pointing in the same direction. The open-source pivot inside Chinese AI did not originate from a strategic planning document in Zhongnanhai. It originated from financial pressure and geopolitical constraint, and it became something far more powerful than either its architects intended or its critics anticipated. When the United States began restricting exports of advanced semiconductors to Chinese firms, NVIDIA's A100 and H100 chips, the hardware that trains frontier models, Chinese laboratories faced a structural problem. Training the largest models requires enormous compute. Without access to the most capable chips, Chinese labs would fall behind on the raw scale of model development. The response was not to find a way around the hardware restriction immediately. The response was to make the existing hardware work harder. DeepSeek, a Chinese laboratory backed by the quantitative hedge fund High Flyer, released a series of models in late 2024 and early 2025 that demonstrated training efficiency gains that surprised Western researchers. DeepSeek's R1 model achieved performance competitive with models from OpenAI at a fraction of the training cost, using architectures that compensated algorithmically for reduced compute availability. The techniques, mixture of experts' architectures, optimized attention mechanisms, aggressive distillation methods, were not secret. They were published. They were absorbed by the broader AI research community within weeks. Open source release was initially a cost strategy. Chinese labs could not charge what OpenAI charged. American firms had established relationships with enterprise customers, had integrated billing infrastructure, had legal and compliance frameworks built around Western regulatory environments. Competing in that market directly was expensive. Giving models away for free and capturing developer mindshare was cheaper. It worked. By the end of 2025, approximately 1/3 of all global AI usage involved Chinese open-source models. In countries like Nigeria, Malaysia, and Brazil, building AI applications on Chinese models ran more than 90% cheaper for developers than building on OpenAI. That price differential did not require a choice between equivalent products. It offered a cheaper product that, on the tasks most developers actually needed, coding assistance, document processing, language translation, customer-facing chatbots, performed comparably. Beijing watched this dynamic and recognized its geopolitical dimension. When U.S. export controls threatened to cut Chinese firms off from Western model infrastructure, from API access, from cloud services, from the ecosystem of tools built around American foundation models, open-source release transformed from a workaround into a countermeasure. If Chinese models were already embedded in the development stacks of 1,000 companies across the global south, those companies did not need to choose sides. They had already, functionally, chosen. Alibaba's Qwen team understood this dynamic explicitly. The billion download figure is not a vanity metric. It represents a billion instances of developers building workflows, companies structuring products, and institutions designing systems around a Chinese model architecture. Switching costs accumulate. The longer that ecosystem persists, the harder it becomes to displace. The geopolitical reframing of open-source AI happened fast. A strategy adopted for cost reasons became, within 18 months, one of the most effective tools for capturing the AI infrastructure of the developing world. The Biden administration's October 2022 export controls on advanced semiconductors were described at the time as the most aggressive use of export restrictions in decades. The stated goal was to slow China's access to the compute required for frontier AI development and advanced military applications. The controls targeted not just chips, but the equipment used to manufacture chips, the software used to design them, and the personnel permitted to assist Chinese firms in operating them. The intent was architectural: remove the input, constrain the output. By 2026, those controls were assessed by multiple analysts as largely beginning not to work. The specific mechanism of failure was not smuggling, though that occurred. The mechanism was engineering. Huawei's Ascend chip line exists because NVIDIA's chips became inaccessible. Ascend chips are slower than NVIDIA's H100 on raw throughput metrics. They have higher latency in certain operations. Their software ecosystem is less mature. These are real disadvantages. Huawei's engineers treated them as engineering problems. Software layers compensated for latency. Architectural modifications distributed workloads differently. Parallelism techniques that Western researchers had developed for other reasons were adapted to fit the constraints of the available hardware. The result was not parity with NVIDIA. The result was sufficiency. Models trained on Ascend clusters at China's leading laboratories were competitive on the benchmarks that mattered. The hardware gap, which export control architects had counted on as a hard ceiling, turned out to have a software flaw that Chinese engineers were highly motivated to raise. This dynamic, using algorithmic and architectural innovation to compensate for hardware restrictions, has a precedent. During the Cold War, Soviet engineers developed computational workarounds for restricted access to Western technology across multiple domains. The workarounds were inferior. They were also functional. Sufficiency in an adversarial context does not require superiority. The 2-week window in April 2026 illustrated how fast this process had accelerated. 3 Chinese laboratories, releasing coding AI tools in rapid succession, all open source, all benchmark competitive, demonstrated something beyond individual model quality. They demonstrated a production cadence. The ability to ship competitive models repeatedly, quickly, and cheaply is as strategically relevant as the ability to ship a single superior model. The United States leads on frontier capability at the margin. China leads on deployment velocity at scale. The compute gap also has a second vulnerability. It assumes that the restrictions hold. Export controls are enforced imperfectly. Chips designated for markets outside China are transshipped. Firms nominally unaffiliated with Chinese AI development acquire restricted hardware through intermediaries. The Department of Commerce has expanded the scope of controls repeatedly since 2022, but each expansion is followed by a period of adaptation. The engineers move faster than the regulators. American AI laboratories retain genuine advantages. Characterizing the current state of competition as parity misrepresents the evidence. OpenAI, Google DeepMind, and Anthropic operate at the frontier of model capability on the tasks that are hardest and most strategically sensitive: complex scientific reasoning, autonomous agent behavior, multimodal integration at high resolution. The gap on these specific tasks, as opposed to general coding benchmarks or document processing, remains measurable. The research talent density at these institutions, built over decades through university pipelines, immigration, and competitive compensation, has not been replicated at equivalent scale in China. The semiconductor advantage is more durable than export control critics suggest, even as its durability is contested. TSMC's 3-nanometer fabrication process, which produces the chips that power NVIDIA's most advanced systems, remains inaccessible to Chinese manufacturers. SMIC, China's leading chip fabricator, achieved 7-nanometer production in 2022 using equipment workarounds, but the jump from 7 nanometers to 3 nanometers involves not just better machines, but entirely different process chemistry. That gap is measured not in months, but in years, and it constrains the theoretical ceiling of Chinese chip performance, regardless of software compensation. NVIDIA's software ecosystem, CUDA, the programming framework that developers have built AI tools on for 15 years, represents an accumulated infrastructure advantage that is genuinely difficult to replicate. Chinese developers can run models on Ascend chips, porting existing tools, libraries, and workflows to a different architecture requires effort that slows iteration. The ecosystem moat is real, even if it is not impenetrable. The intelligence and defense applications of frontier AI, the ability to process satellite imagery at scale, to automate signals intelligence analysis, to run autonomous system coordination, remain areas where American classified programs are believed to hold substantial leads. The evidence for this assessment is necessarily indirect. Classified programs do not publish benchmark results, but the institutional infrastructure for classified AI development in the United States, the Defense Advanced Research Projects Agency, the Intelligence Advanced Research Projects Activity, and the network of cleared contractors has no evident Chinese equivalent at comparable organizational maturity. Huawei's Ascend roadmap includes progression toward more sophisticated multi-die chip architectures that would close the raw compute gap further. The trajectory is upward. The current distance from the frontier is not zero. These are both true simultaneously, and the tension between them is precisely where the strategic uncertainty lives. The most consequential consequence of China's AI trajectory has nothing to do with large language model benchmarks. It has to do with infrastructure dependency, and the geography of that dependency is shifting in ways that American policy has not fully processed. By 2026, Chinese open-source AI models had achieved deep penetration across sub-Saharan Africa, Southeast Asia, and Latin America, regions that collectively represent the majority of global population growth over the next 30 years. The mechanism was price. The implication is architecture. When developers in Nairobi build a fintech application on Qwen, when hospitals in Jakarta deploy diagnostic tools on a DeepSeek-derived model, when government agencies in Brasilia process documents through Alibaba's cloud infrastructure, the technical dependencies that accumulate are not neutral. They encode choices about data routing, about model update channels, about the standards and protocols that govern how AI systems behave. The United States built its technological influence in the second half of the 20th century, partly through the same mechanism. American software became the default. American networking protocols became the infrastructure. American cloud platforms became the substrate. The costs of switching away were high enough that switching rarely happened. China is executing an analogous strategy with AI infrastructure, and the price differential makes the initial adoption decision straightforward for resource-constrained institutions. This is the dimension of the competition that the 18-month framing obscures. A gap in frontier model capability matters enormously for a narrow set of applications. A gap in global deployment footprint matters for everything else. China's open-source, low-cost AI is not competing for the marginal researcher at a well-funded American university. It is competing for the next billion users of AI systems in markets where the cost difference between American and Chinese options is not 10% but 90%. The policy response from Washington has been incremental. Export controls have been tightened repeatedly. The Chips and Science Act of 2022 committed $52 billion to domestic semiconductor manufacturing with the goal of reshoring advanced fabrication capacity. Allied coordination through mechanisms like the Chip 4 Alliance, linking the United States, Japan, South Korea, and Taiwan, has attempted to create a coherent export control architecture that is harder to circumvent through transshipment. These measures address the supply-side constraints on Chinese AI development. They do not address the demand-side dynamics that are reshaping global AI adoption. Slowing the production of Chinese AI hardware does not reduce the deployment of Chinese AI software in markets that have already chosen it on price. The two levers operate in different domains on different timescales. Eric Schmidt's revision from 2 years to 6 months captures one dimension of the change. The compression of frontier capability estimates is significant, but the more durable strategic shift is the one that does not appear in any capability estimate. A parallel AI ecosystem built on Chinese architectures, governed by Chinese update cycles, distributed through Chinese cloud infrastructure, now embedded in the development stacks of thousands of institutions across the developing world. That ecosystem did not require China to win any specific benchmark competition. It required China to be cheap enough, fast enough, and present enough at the moment when the Global South was making its first infrastructure choices about artificial intelligence. That moment has largely passed. The choices are accumulating into dependencies. The dependencies are hardening into architecture. The gap was 18 months. The gap is closing. Neither of those facts is the most important fact. The most important fact is that while analysts were measuring the distance between frontier models, a different competition was being decided in places where frontier models were never the relevant variable.